Hello, my name is Onobrato Das. I'm a PhD student at the School of Information at University of Texas at Austin. Today, I'll talk about our paper published in ACL 2022 titled Prototype: Explaining Model Decisions with Prototype Tensors. If you look at the modern pre-trained language model in NLP, in most of the times we see that given an input, we have a high performing classifier that gives an output about what category the sentence might belong to. But most of these cases, when we use pre-trained language model for classification, we don't have a clarity on how the model might have come to that particular decision. Today, users have a lot of questions when they consume machine learning uh, in general. Questions such as why certain decisions are made, why not something else, when the model succeeds, when the model fails, when the model can be trusted, and when the model makes a mistake, how the error can be corrected. However, if we put explainability at the center, which is crucial for practical use by people, a user potentially would have answers to at least some of these questions. To reiterate, they will understand when the model succeeds, when it fails, and when to trust the model, and to uh, when to override its mistakes. Even though there are high performing models, tasks that are complex for current models and the decisions that are high stakes, we still have a human in the loop that takes the ultimate decision. For example, high stake tasks such as hiring or content moderation, in these cases, explainability becomes even more important. Especially in those contexts, why the model is wrong or whether the model is doing the right thing for the right reason becomes particularly critical. If we look at the conventional methods, such as nearest neighbor, decision tree, or logistic regression, these comes with built-in explainability that helps users kind of understanding or forming an understanding about how the model makes a decision. However, the con is that with current state-of-the-art NLP tasks, these models do not perform as well. And in the modern NLP, we have seen a rise of large-scale pre-trained language models that provides powerful representations. And these powerful representations lead to superior performances. But the biggest con for in this particular scenario is that these models are black boxes. Hence, it is difficult to understand when they might make mistakes and why so. Given this context, we propose ProtoTEx. It's a new method for explainability, where given an input, not only it predicts what the output is, also it provides explanation in the form of key examples. Here, let's imagine the task is predicting exaggeration. Given this input sentence, his ego is the size of Mount Rushmore. So here, the size of Mount Rushmore is clearly a framing of exaggeration. And you see that the model has picked up examples such as this homework assignment will take years to finish, which is another example of exaggerating a text. So Prototype, the idea is that it combines the best of both worlds from pre-trained language models and the explainability of the classical model and provides a transparent and explainable method while keeping the accuracy similar to that of the state-of-the-art language models. The rest of the talk is organized as follows. First, I discuss the key idea behind prototype networks. Then I describe the model architecture and training. I discuss the evaluation for this method through two different facets. One is predictive performance and the utility of the explanations. And I conclude my talk by reiterating our findings. So Lee et al. First introduced the idea of prototype networks for computer vision tasks. Prototypes, tensors are essentially cluster heads and that form unsupervised soft clusters in the training examples, and prototypes are the cluster heads for these soft clusters. And one idea behind this inference using prototypes is kind of similar to how inference is done with k-nearest neighbor. Now, directly applying this prior work from Lee et al. To NLP does not perform as good. And To match the state of the art performance for natural language processing, we experiment with several different um, ideas. First, we implement this prototype network in the context of transformers. And then we experiment with different normalizing distance vectors and different initialization of the prototypes. And finally, we propose a novel interleaved training algorithm that helps us boost the performance and match with state of the art. I will not be discussing this step in details. Please refer to our paper for more details for each of these steps. Now let's take a look at the model architecture and also go through the training mechanism for this model. So first, given a test instance, we pass that through an encoder, and this encoder could be anything of your choice or any encoder that comes out in the future. And then we have prototypes that are of the same dimension as the encoder representation. And once we have these prototypes, and you can recall here that the prototypes are essentially soft clusters. That's what the red dots and the green dots represent around these prototypes. Now we calculate the L2 distance between the encoder and the prototype. And we do this for the encoder representation and each of these prototypes. Once the distances are obtained, a linear layer takes in all these distances, and that passes through a softmax for the final prediction decision. Now, once we have the prediction decision, how do we obtain the explanations? For that, we first look at the most influential prototypes for a particular test example. To identify the most influential prototype, we select a multiplication between the distance vector and the weights from the linear layer. So it's a combination of di and the w, the weights from the linear layer, that gives us the most influential prototypes. And now once the prototypes are ranked, for each prototype, we will be able to identify what is the closest training example. So let's say we identify k top prototypes, and for k top prototypes, we identify m top examples, and that becomes our explanation. Now, how do we train this model? The loss function looks like the equation displayed on the slides. I'll break it down now. So first, the cross entropy loss that is used for binary prediction and propagating the binary prediction error through the network. And the second set of losses, that is LP1 and LP2, are prototype losses. The idea behind prototype losses is what enable the soft clustering. So this basically minimizes this L2 distance between the prototypes and the training example, and also encourage the input examples to form these soft clusters. Specifically, LP1 minimizes the L2 distance between the prototype and the training example by freezing the training example. So when LP1 is being trained, at that time encoder is not fine-tuned, and we just push the prototypes closer to the encoder. And in LP2, we freeze the prototypes and encourage the training example by fine-tuning the encoder final layers to form the soft clusters around the prototypes. To evaluate this model, we first look at the predictive performance. And the task that we pick for this is propaganda detection. It's a dataset proposed by De San Martino et al. In EMLP 2019. And this task, we particularly pick this task because it's a complex prediction task, and it requires certain level of expertise about propaganda framing for a non-expert users to identify what propaganda framing actually is. Evidently, the data set that we use is expert annotated from sentence crawled from news article on the web, and we have about 21,000 sentences in this data set. The binary prediction task that we evaluate on is, does a sentence contain propaganda? So here are some examples. I'll just read one of them for the purpose of this talk. That Munchin says Democrats acted like babies at the State of the Union. Now, acted like babies is an example of a propaganda framing. To compare the predictive performance, we look at several baselines. The first one is, if we just pick the majority class, then we'll get an F1 score of about 53. If we fine-tune BERT on this data set, we get an F1 score about 73. When we fine-tune BART on this data set, we get an F1 score of 75. To look at some alternative for case-based reasoning or similar explainable alternative, we take BART representation and feed it through a k-nearest neighbor algorithm, and we achieve about a 67 F1 score in that case. And then finally, we see ProtoTEx, that is our model that achieves a 75F1 score and matches the accuracy of BART. Now, are these explanations useful? To understand that, we look at two different facets. One is model understanding. Do explanations help users predict the model's classification output? And the second aspect is explanation utility, where we examine whether these explanations help users to identify propaganda text better. To evaluate the explanation, we show users the input and the similar explanations. So in the input, if you recall this diagram from before, we give this input and a set of examples. And we mask out the prediction, where the prediction is, you see, it's in question mark. Given this, for model understanding, we ask our participants, given the example above, what do you think the model has predicted? And for explanation utility, we ask a different question. What do you think is the correct label? And this is about the ground truth. And note that here we also vary a certain prediction outcome, where we show that to some set of users that the model has predicted this text as propaganda or not, and some set of users, they do not see the model prediction. Let's take a look at the results for model understanding first. So given a model, when we show randomly drawn examples to the users, we see that users are more often incorrect, or they don't have any idea about what the model may have predicted. And when we show them explanations for the cases where the model made incorrect prediction, we see kind of a similar results. These numbers look exactly the same because of they're rounded up, but they're kind of in the similar ballpark in terms of the percentage of users. And now when we show users the examples when the model made correct prediction, whether something is propaganda or not, we see that the graph flips and users are more correct. So the explanations are kind of helpful in model understanding only when the model is correct. A future work could actually look into help users better recognize when the model is wrong. And for explanation utility, we compare against a few baselines. The first one is we give only a particular sentence from this dataset to the user and ask them whether this is propaganda or not. And then in a second baseline, we show them that sentence and show them a set of random examples that are drawn from the dataset. And you see that showing random examples as explanations is actually hurting the performance. Now, in this experiment, we vary the model performance post-hoc. That is, we only analyze the data where the model is 50% of the time the model is correct, or 75% of the time is correct, or the model has 100% accuracy. And here, the 75 box is marked to indicate that this is where, in the ballpark, this is where our model performance is as of today. Now, given this varying model performance, when we provide only explanations, we see that ProtoTEx retrieved examples are more helpful than randomly retrieved examples. And then we see that the explanation utility increases with model performance. Now, when we add back the model prediction for the users who see the model predictions along with the explanations, we see that this already shows an improvement even at the 50% accuracy. And when we look at 75% accuracy, this is the first time we see that the explanations are more useful and compared to both the baselines that we have shown here. So at this current performance, we observe that better accuracy compared to all the other baselines. Now, if we had a way to improve the model accuracy even further, and if we want to get a sense of what the upper bound might look like for user performance, given a much higher model performance, we see that there is a vast improvement when there is prediction and explanation present for identifying whether a text is propaganda or not. To conclude this talk, we introduce a novel method, ProtoTEx, that provides training example-based faithful explanations. And ProtoTEx matches the predictive performance of the underlying encoder, in this case, BART, with added benefits of faithful explanations. Human evaluation shows that the explanations are helpful in forming model understanding when the model is correct in terms of making its prediction. And further, we see that the explanations improve user accuracy on the downstream complex propaganda detection task, specifically for non-expert users. Here is the paper link, and the code is available on GitHub. I'd like to thank Texas Advanced Computing Center for supporting with the resource for this research. Additionally, I'd like to thank Good Systems, Knight Foundation, Micron Foundation, Wipro, and National Science Foundation for funding my work. Thank you for listening. Please send me any questions you might have on Twitter or via email.